Hello, everyone. Tonight, we will embark on a journey into the mysterious depths of the universe. Enjoy listening. Galaxies of thought don't always arrive with noise. Sometimes they arrive as a whisper, quiet facts that feel almost too strange to be real, yet grounded in the careful work of modern science. Tonight's journey is built like that. A series of gentle, cosmic whispers. Some of them might widen your eyes for a moment. And then, if you let them, they can also soften your breathing and make the universe feel less like a cold void and more like a vast, ancient home. You don't need to remember everything. You don't need to keep up. This is designed for rest. Let the ideas float by at a calm pace, the way distant lights drift past a window at night. If you fall asleep halfway through, the cosmos will not be offended. It has waited billions of years to be understood. It can wait a few more minutes. Begin with the simplest motion. Imagine lifting your gaze. Not dramatically, not as a grand gesture, just a small tilt of attention upward, outward, toward that familiar ceiling of night. In daily life, we often forget to look up. We live inside schedules, screens, errands, worries, and the constant hum of human noise. Yet above all of it, the universe continues silent, immense, and astonishingly indifferent to our rushing. Not indifferent in a cruel way, indifferent in a calm way. The kind of calm that can be comforting if you let it. The night sky is not only scenery, it is context. It is where every atom of your body ultimately comes from, where the laws that shape your life were written, and where time moves at a scale so long it makes our anxieties feel lighter. With that softness in mind, let's listen to 7 cosmic whispers, surprising truths that can unsettle the mind for a second, and then settle it deeper into wonder. Somewhere in the Milky Way, perhaps not very far in cosmic terms, there may be planets traveling alone. We usually picture a planet as something loyal, held close by the warmth of a star. A planet, in our familiar story, belongs to a system. It circles a sun. It experiences mornings and evenings. It has seasons, or at least a rhythm of light and shadow. But the galaxy may be filled with worlds that have no sun at all. Astronomers call them rogue planets, or free-floating planets, objects with planetary mass that drift through interstellar space without orbiting a star. How many are there? The honest scientific answer is that the exact number is still uncertain because they are difficult to detect. They don't shine like stars. They don't reflect much light in the darkness between stars. They are, in many cases, almost perfectly hidden, and yet multiple lines of evidence suggest they could be very common, possibly billions, in our galaxy alone, perhaps even more. Some studies have hinted at numbers that sound unreal, though the estimates depend on assumptions and the limits of our measurements. The important part is not the exact count. The important part is that the galaxy may not be neatly organized into only sunbound systems. It may also contain countless solitary travelers. How does a planet become a wanderer? One pathway is chaos in young planetary systems. When planets form, they form in disks of gas and dust, swirling around newborn stars. In that early period, gravitational interactions can be intense. Young planets can tug on each other, trade energy, and scatter. Sometimes, a planet can be flung outward so strongly that it escapes the gravity of its star, entirely exiled into the space between stars. Another pathway is more subtle. In some cases, objects can form in collapsing gas clouds in a way that produces planetary mass bodies without ever becoming full stars. The boundary between planet and brown dwarf and low-mass star can be complicated because nature does not always respect our labels. What matters is that the galaxy can produce dark, cold worlds in more than one way. Now let your imagination rest on a single rogue planet for a moment. No sunrise, no sunset, no warm daylight spilling over mountains, no familiar anchor in the sky, only distant starlight, faint, scattered, and cold. Only the slow passage through interstellar darkness, where even the densest regions are emptier than any vacuum humans build on Earth. It sounds like absolute loneliness. And yet, even a rogue planet might not be completely dead. Some could retain heat from their formation for a long time, insulated by thick atmospheres. Some might have internal heating from radioactive decay. And in very speculative ideas, a rogue planet with a sufficiently dense atmosphere could trap enough heat to keep subsurface oceans from freezing solid. These are not confirmed habitats, just possibilities that show how. Lift your attention upward for a moment, not with effort, not like a task, but like a slow, natural motion. In the middle of a noisy day, we forget how easy it is to do this, how instinctive it once was to look at the sky and feel that familiar, quiet question forming in the chest. What is all of this, really? We move through schedules and messages and bright screens, and we become experts at focusing on what is close. But above the roofs and trees and streetlights, above the weather and the airplanes, the universe continues in an older rhythm, silent, enormous, and strangely calming once you stop trying to measure it with the clock in your hand. Tonight is a gentle walk through that older rhythm. It's science, but spoken softly. It's wonder, but not rushed. You don't need to memorize anything. You don't need to keep up. If your mind drifts, that's perfectly in character for a universe where even galaxies drift. Think of this as listening to the cosmos the way you might listen to wind in a distant field. Sometimes you notice patterns. Sometimes it's only a soothing texture in the background. The first thing to hold lightly is that the night sky isn't just scenery, it's context. It's a record of where your atoms came from and what the laws of nature can build when they're given enough time. When you look at the stars, you are not looking at decorations pinned onto a black ceiling. You're looking at distant suns, yes, but also at time. Light takes time to travel. Every photon that reaches you has crossed space for years, centuries, sometimes thousands or millions of years, carrying a message from the past. And then there's the deeper thought, the one that can feel unsettling for a second and then oddly comforting. You are part of this, not metaphorically, literally. The chemistry of your body is a chapter in the same cosmic story as nebulae and supernovae and galaxies. The universe is not something happening out there. It's also happening in you, in the sense that you are made from it and governed by it. You are a local pattern made of ancient material, temporarily aware, briefly warm, allowed to rest. With that gentle foundation, let's listen to several cosmic whispers, facts that can steal your sleep if you chase them too sharply, but that can also cradle your mind if you let them arrive slowly. Somewhere in the Milky Way, there may be planets traveling alone. We are used to planets as companions. A planet, in our mental model, belongs to a star the way a boat belongs to a harbor. It circles, it returns, it has a reliable source of light and warmth. Our own planet's daily cycle is built on that relationship. Sunrise and sunset, seasons, the long gradual drift of constellations over the year. But the galaxy does not always keep families together. Astronomers have strong reasons to think that the Milky Way contains a population of rogue planets. Planets not bound to any star, drifting through interstellar space. Detecting them is difficult, precisely because they don't glow the way stars do. They are cold, dark, and far away. Yet, they reveal themselves indirectly, most famously through gravitational microlensing. When a massive object passes in front of a distant star, its gravity can bend and focus the star's light, making the star brighten briefly. If the lensing object has planetary mass, the brightening can be subtle and short-lived. Catching these events requires monitoring huge numbers of stars for long periods with careful statistics and a bit of patience. It's a method that feels fitting. To find lonely planets in darkness, we watch for tiny, temporary changes in light. How do planets become rogues? One pathway is exile. In young planetary systems, bodies form inside disks of gas and dust, swirling around newborn stars. Those early environments can be crowded and chaotic. As planets grow and migrate, they tug on each other gravitationally. Orbits can shift. Resonances can build tension like a tightening string. Sometimes the system stabilizes into a long-term architecture. Sometimes it doesn't. A close encounter between massive planets can fling one outward. With enough energy, a planet can exceed the escape velocity of the system and drift away into the space between stars. Another pathway is solitude from the beginning. Nature makes objects in a continuous spectrum of masses. A collapsing cloud fragment might fail to gather enough material to ignite sustained hydrogen fusion, so it never becomes a star. It might become a brown dwarf, or it might end up with planetary mass. Whether we label such an object a planet can depend on formation history and definitions that scientists still debate. But the existence of free-floating planetary mass bodies is plausible, and evidence suggests they are real. Now, let your mind rest on the image of one such world. No sunrise, no sunset, no warm star hanging large in the sky. The stars are still there, but they are distant pinpricks, faint and cold. The background is a darkness so clean it almost feels like a substance. The planet's surface, if it has one, could be frozen solid. Its atmosphere, if it has one, could be thin or thick or absent. Its landscape might never feel a day. It sounds like absolute loneliness. But even here, physics leaves a door cracked open to complexity. A rogue planet may retain internal heat left over from formation for a very long time, especially if it is massive and insulated by a thick atmosphere. Radioactive decay in the planet's interior can provide long-lived heating, the same way it contributes to Earth's internal warmth. Some speculative models suggest that with a sufficiently dense hydrogen-rich atmosphere, a rogue planet might trap enough heat to keep a subsurface ocean from freezing completely. Not because starlight warms it, but because its own interior, slowly and steadily, refuses to go fully cold. This is not a promise of life. It is only a reminder that nature is inventive. Even in darkness, there can be gradients of heat and chemistry. Even without a sun, a world can have a story alone. And if you feel a quiet sadness for those drifting planets, that's a very human response. But there is also an unexpected comfort in the thought. Not everything in the galaxy depends on the same conditions. There are many ways to exist, many ways to travel, many ways to be a world. Now, let that lonely world drift farther away in your imagination until it becomes just one possibility among billions, a small dark bead on an invisible thread. Because the next whisper is closer than any star. It's happening through you, right now, without sensation, without sound, without permission. Dark matter. The name itself sounds like a myth, but it's a scientific placeholder for a very real mystery. We call it dark because it doesn't interact with light the way ordinary matter does. It doesn't shine. It doesn't reflect. It doesn't conveniently announce itself in telescopes. And yet, if you watch the universe carefully, you see that something unseen is adding gravitational pull. One of the cleanest clues comes from galaxy rotation. In a spiral galaxy, stars orbit the center. If most of the mass were concentrated in the luminous disk and bulged the stars and gas we can see, then you would expect orbital speeds to drop with distance, similar to how the outer planets orbit more slowly than inner ones in the solar system. But when astronomers measure galaxy rotation curves, they often find that orbital speeds remain roughly flat, far from the center. The outer regions move too quickly to be held by visible matter alone. Something else must be contributing mass, an extended halo of unseen matter surrounding the galaxy. Then there's gravitational lensing. Mass bends space-time, and space-time guides light. When a massive cluster of galaxies sits between us and more distant galaxies, it can distort and magnify the background light, creating arcs and multiple images. By measuring how strong that lensing is, astronomers can map the mass distribution. Often, the mass required to produce the lensing is far greater than the visible matter present. Again, unseen mass. And then there is the cosmic microwave background and the growth of large-scale structure. The early universe left behind a faint afterglow microwave radiation filling all of space. Its tiny fluctuations carry information about the universe's composition. The patterns we observe strongly suggest that ordinary matter atoms makes up only a small fraction of the total matter content. The rest behaves gravitationally, but not electromagnetically in the usual way. Put these lines of evidence together, and a consistent picture emerges. The universe seems to contain a large amount of matter that does not interact with light, yet contributes gravity. We call it dark matter. What is it made of? We still don't know. That isn't a weakness of science. It's a boundary line, one of the places where curiosity remains alive. Scientists have proposed many candidates, new particles that interact very weakly with ordinary matter, particles that were produced in the early universe and linger today, or modifications to gravity itself. Though many observations favor some form of unseen matter, experiments deep underground look for rare collisions between dark matter particles and atomic nuclei, protected from cosmic rays and background radiation. Telescopes search for indirect signatures, radiation that might result from dark matter annihilation or decay, depending on the model. Particle accelerators explore the energy scales where new physics might appear. So far, no definitive detection, but the search continues with remarkable precision. Now, about the idea that dark matter passes through you. If dark matter is made of weakly interacting particles, Earth is moving through a sea of them as it orbits the Milky Way. Under such models, huge numbers of dark matter particles could pass through your body every second. They pass through walls and oceans and mountains. They pass through planets as if planets were thin mist. They rarely interact, which is why you don't feel them. Their presence is inferred from their collective gravitational behavior, not from direct sensation. It can sound eerie cosmic visitors moving through you like ghosts, but there is a calmer way to hold it. Think of dark matter as invisible architecture, an unseen framework shaping galaxies and clusters, helping them form and stay bound. You are lying on a small planet inside a luminous galaxy, and that galaxy is embedded in a vast halo of something you cannot see. You are supported, in a cosmic sense, by an ingredient of reality we are still learning how to name. There is humility in that, and a quiet peace. Not everything that holds you has to be visible. Now, let the mind shift gently from the unseen to the crystalline. Because the universe sometimes builds objects that sound like fantasy, until you remember that fantasy is often just unfamiliar chemistry under unfamiliar pressure. Diamond worlds. The phrase is poetic, but the underlying idea is grounded in materials, science, and astrophysical possibility. Carbon can exist in many forms: graphite, diamond, amorphous carbon, complex organic molecules. Under high pressure, carbon tends to favor crystalline structures. Deep inside a planet, pressures can reach millions of atmospheres. In such conditions, chemistry becomes architecture. In some planetary systems, the ratio of carbon to oxygen in the protoplanetary disk could be high enough that carbon-rich solids dominate. In those environments, planets might form with interiors very different from Earth's silicate-rich makeup. Instead of rock dominated by oxygen and silicon, you might get structures with more carbides and carbon phases. Under the right pressure-temperature conditions, large fractions of a planet's interior could become diamond-like carbon. There are also exotic cases involving stellar remnants. A pulsar is a rapidly rotating neutron star the dense core left behind after a massive star collapses. Some pulsars have companions. In certain scenarios, a companion can be stripped down to an ultra-dense remnant, possibly rich in carbon. Under immense pressure, that carbon could crystallize. The object might, in a sense, be a huge crystal, though crystal here does not mean a sparkling gemstone on a velvet pillow. It means the arrangement of atoms under pressure, a planetary scale material phase. Would such a world glitter? Probably not in the way our imagination hopes. Many of these objects would be extremely hot, irradiated, or covered by other layers. Surfaces in space are altered by impacts, radiation, and chemistry. A diamond planet may not be visibly shiny, but the deeper whisper remains. The universe can build worlds from ingredients arranged in ways that feel surreal to us. And that is a recurring theme tonight. The cosmos doesn't care what sounds improbable. If physics allows it and time provides the chance, nature will try it. Now let's expand outward again, beyond planets, beyond stars, toward the largest architecture we can map, the cosmic web. If you could step far outside the Milky Way, far beyond any normal sense of distance, until individual galaxies became points, and then until those points became part of a larger pattern, you would not see randomness. You would see structure. Galaxies cluster. They form groups. They gather into clusters with hundreds or thousands of members. And on even larger scales, clusters connect along filaments, long, thread-like structures of matter. Between these filaments are voids, enormous regions with far fewer galaxies. This is not an artistic metaphor. It is measured. Surveys that map millions of galaxies show this network. Computer simulations of the universe using the known laws of gravity and a mixture of dark matter and ordinary matter naturally produce similar patterns. The cosmic web emerges from a simple principle. Gravity amplifies small differences, and over time, matter flows toward denser regions. Dark matter plays a crucial role here too, because it does not interact with radiation the way ordinary matter does. It forms structures early and efficiently. It creates gravitational wells and filaments. Ordinary gas falls into those wells, cools, and forms stars and galaxies. In this picture, dark matter is the scaffolding, and galaxies are the lanterns hung on that scaffold. Now comes an observation people often find unsettling in a strangely beautiful way. The cosmic web nodes connected by filaments can resemble other networks we know. Neural networks in the brain, fungal mycelium in soil, river systems, lightning branching. This does not mean the universe is literally a brain. There is no evidence that cosmic filaments think. The similarity is more subtle and more general. When systems grow under constraints and flows, networks are a common solution. Nature loves networks. The brain forms networks because biology evolves efficient communication and integration. The universe forms networks because gravity and expansion organize matter into efficient pathways of flow and accumulation. Different rules, different materials, similar geometry. It's as if nature has a small library of shapes it returns to across scales. And that thought can feel strangely restful. It suggests a kind of unity, not mystical, but structural. The same universe that can build a thinking brain can also build a cosmic web that looks, at a glance, like the architecture of thought. You are a network looking at a network. The universe is studying itself through one of its own patterns. Now let the cosmic web fade into a softer background and listen to the next whisper one about sound in a place where sound, as we know it, cannot travel. Space is close to a vacuum. Sound waves require a medium air, water, solid material particles that can bump into each other and carry vibrations. In empty space, there is no air to transmit sound. So, space is silent to human ears. And yet, stars have rhythm. Stars have oscillations. Stars have something like music, not because they broadcast sound through space, but because their interiors vibrate in measurable ways. This is the science of asteroseismology. A star is not a rigid sphere. It is a dynamic ball of plasma. Heat rises and falls in convection. Pressure and gravity tug against each other. Rotation introduces subtle distortions. Magnetic fields thread through hot material. These processes can generate waves inside the star, pressure waves and gravity waves, creating oscillation modes that make the star's surface move up and down by small amounts. In the Sun, these oscillations are observed as tiny changes in surface velocity and brightness. The surface can rise and fall by just a few meters in certain modes, small compared to the Sun's size, but measurable with sensitive instruments. By analyzing the frequencies of these oscillations, scientists infer the Sun's internal structure, much like seismologists use earthquakes to probe Earth's interior. Different oscillation frequencies correspond to waves that penetrate to different depths. The pattern of frequencies reveals the sound speed profile inside the star, which depends on temperature and composition. This allows astronomers to measure properties that would otherwise be inaccessible: the depth of the convection zone, internal rotation rates, and details of stellar evolution. Other stars oscillate too. Some pulsate in strong, regular ways. Cepheid variables expand and contract with stable periods, and because their pulsation period is related to their intrinsic brightness, they become crucial standard candles for measuring cosmic distances. Other stars have subtler oscillations detected by space telescopes like Kepler and TESS, which can measure brightness changes at the level of parts per million. And sometimes, for public outreach or artistic exploration, scientists and educators sonify these oscillations, shifting frequencies into the range of human hearing. What you hear is not sound traveling through space. It is data translated into sound, but it is still a translation of something real, a star's internal rhythm. The whisper here is gentle and sleep-friendly. Even where there is silence, there is motion. Even without air, there is vibration. Even without ears, the universe has resonance. And because you are made of matter, obeying the same physical laws, your body also has rhythms: breath, heartbeat, brainwaves. You are another kind of oscillating system, and sleep is one of the ways your internal rhythms find balance. Now we turn to a whisper about endings, because the universe has many ways to close a chapter. We often imagine a star's death as spectacular. A massive star runs out of fuel in its core. The outward pressure drops, gravity wins, the core collapses, and a supernova erupts, scattering heavy elements into space. In that picture, the ending is bright. It is loud in light. It announces itself across galaxies. And many stars do die like that, but some may not. Some massive stars might collapse directly into black holes with little or no bright supernova. This idea is sometimes described as a failed supernova, though the word failed says more about human expectations than about physics. From the universe's perspective, it's simply a different pathway. Core collapse supernovae are complex. When a star's core collapses, it forms a neutron star or a black hole. A shock wave forms and can, under the right conditions, propagate outward and blow off the star's outer layers. Neutrinos, nearly massless particles produced in enormous numbers during collapse, play a crucial role in the energy budget and shock revival. Rotation, magnetic fields, and the exact structure of the star's layers also matter. In some cases, the shock may stall, and the star may fail to explode brightly. The core continues collapsing into a black hole, and much of the star's material may fall inward rather than being ejected. How would we know? One approach is patient monitoring. Astronomers watch nearby galaxies for massive stars and keep track of them over years. If a massive star that was clearly present simply disappears and does not produce a typical bright supernova, that could be evidence of direct collapse. There have been candidate cases where a luminous star faded away and stayed gone, suggesting a quiet birth of a black hole. The evidence is still developing, and this remains an active area of research. But the possibility is strong enough to reshape how we think about stellar death. The whisper here is poetic, but grounded. Not every powerful change in the universe is accompanied by fireworks. Some endings are quiet. Some stars go out like a candle in windless air, simply vanishing into gravity. And if you let that idea rest inside you, it can become surprisingly calming. It suggests that silence is not emptiness. Silence can be a transition. Darkness can be an event. The universe can be dramatic without being loud. Now we arrive at the whisper that feels the most personal. You are made of star-forged elements. This isn't a metaphor. It's chemistry and cosmic history. The early universe, shortly after the Big Bang, was mostly hydrogen and helium with small traces of lithium. That's it. No oxygen, no carbon, no iron, no calcium, no silicon, no phosphorus. The elements that make rocks and oceans and bones and brains were not present in meaningful amounts at the beginning. They had to be made. They were forged inside stars. In stellar cores, nuclear fusion combines lighter nuclei into heavier ones. In sun-like stars, hydrogen fuses into helium. Later, helium can fuse into carbon and oxygen. In more massive stars, fusion proceeds through additional stages, building heavier elements in shells, neon, magnesium, silicon, until iron forms. Iron marks a turning point. Fusing iron into heavier elements does not release energy, it consumes energy. So when an iron core forms in a massive star, the star is nearing the end of its ability to support itself through fusion. Then come the explosive processes. In supernovae, the immense energy and neutron-rich environments allow heavy elements to form through neutron capture processes. Elements heavier than iron, many of them are created in these extreme moments. Neutron star mergers, when two neutron stars collide, also produce heavy elements in enormous quantities, including many of the rare, very heavy elements we find on Earth. Over time, stellar winds and explosions spread these elements into interstellar space. Gas clouds become enriched. Dust grains form from heavy elements. Molecules become more complex. New stars form from this enriched material, and around those new stars, new planets form. And on at least one of those planets, chemistry organized itself into biology. Your body contains carbon atoms that were cooked in stellar interiors, oxygen atoms that were made through helium fusion, iron that was forged in massive stars and distributed through violent cosmic events, calcium, phosphorus, nitrogen, each with a history older than Earth itself. You are, quite literally, recycled stardust with a nervous system. And there is something deeply comforting in that if you let it be simple. You are not separate from the universe. You are one of the things the universe can do. Not because the universe intended you, but because the same laws that shape stars can, in the right environment, shape life and thought. You are not an outsider looking at a foreign world. You are an expression of the same reality you're trying to understand. Now, let all of these whispers settle together like layers of calm air. Lonely planets drifting between stars, sometimes with hidden warmth deep inside. Invisible dark matter passing through you and through Earth and through the Milky Way, shaping the cosmic architecture while remaining mysterious in its identity. Carbon-rich worlds where pressure sculpts matter into crystalline forms, reminding us that nature's materials are far more varied than what we handle on Earth. The cosmic web, vast and delicate, guiding galaxies into filaments and clusters like dew collecting on threads. Stars that sing through oscillations, revealing their inner structure through rhythm rather than voice. Massive stars that sometimes die without spectacle, folding directly into black holes like secrets kept by gravity. And you built of elements forged in ancient stellar furnaces, resting for a moment in a bright era of cosmic history. Now, if your mind is still awake enough to wonder, consider the gentle background condition that frames all of this. Expansion. The universe is expanding. Space itself stretches. On large scales, distant galaxies recede from each other, not because they are flying through space like bullets, but because the metric of space between them grows. This expansion was discovered through observations that galaxies' light is redshifted. Their spectral lines shifted toward longer wavelengths more strongly for more distant galaxies. The relationship between distance and recession velocity was one of the key discoveries of modern cosmology. Expansion can feel like a cold concept, but it is simply the universe's geometry evolving, and it has consequences over very long timescales. Expansion changes the cosmic environment. Star formation rates have declined since their peak billions of years ago, partly because the universe has expanded and gas has become more diffuse, and partly because galaxies have used up or heated much of their star-forming fuel. In the far future, if expansion continues and accelerates as current evidence suggests, many galaxies will recede beyond our observable horizon. The sky of the distant future could become emptier to observers in a galaxy like ours, with fewer external galaxies visible. But you are here now during what some might poetically call a luminous season. Stars are still being born in nebulae. Galaxies still collide and merge. Heavy elements still circulate. Planets still form. In at least one quiet corner, a mind can lie down and listen to the universe and feel its own breathing slow in response. If that makes your life feel small, let it also make your life feel gentle. Small is not the same as meaningless. A single warm room can matter to the person resting inside it. A brief conscious moment can be precious, even if the cosmos is vast. The universe doesn't have to be personal for your peace to be real. Now, settle into a final, slow image, something you can carry like a soft blanket of thought as sleep approaches. Imagine the Milky Way from far away, a barred spiral galaxy with arms traced by young stars and glowing nebulae, dust lanes cutting dark rivers through the starlight, and a quiet supermassive black hole at the center. Around it, an invisible halo of dark matter extends far beyond the luminous disk, holding the galaxy in a gravitational embrace. Imagine the Milky Way as one lantern among billions, each galaxy a slow machine of gravity, gas, and time. Imagine those galaxies arranged along the filaments of the cosmic web, the vast network that emerged from tiny early fluctuations amplified over eons. Imagine the universe not as empty, but as structured emptiness, space filled with faint radiation, thin gas, invisible matter, and the gentle echo of the early cosmos. Imagine stars vibrating in internal rhythms, revealing themselves through subtle pulses of light, each star a resonant sphere, obeying the same physics that shapes your own beating heart. Imagine some stars ending in bright explosions, scattering the ingredients of future planets, and some ending in quiet collapses, slipping into darkness without spectacle. Imagine rogue planets drifting in the gaps between stars, silent travelers carrying their own histories, sometimes with warmth hidden deep inside. And now, imagine your own body as part of this continuum, a temporary arrangement of ancient atoms, returned to stillness for a few hours. As the planet turns and the galaxy rotates and the universe expands. Your breathing is a small rhythm inside a larger one. Your sleep is not an interruption of the cosmos. It is one of the cosmos's natural patterns, rest and repair, quiet and renewal, cycles within cycles. There is nothing you need to solve tonight. The universe is large enough to hold unanswered questions. It is old enough to wait, and you are allowed to rest inside it, safe, quiet, and gently connected to everything you've just imagined. Let your attention soften. Let the images blur at the edges. Let the cosmic whispers become a steady background hush, like distant surf. And in that hush, allow sleep to arrive the way night arrives in space, without resistance, without hurry, simply as the next calm state in a universe that is always moving, always changing, and always, somehow, steady, sweet dreams.